welcome. We are extremely happy to welcome you to this third iteration of the Gaza Excellence Talks with the Imperial Terence Tao today. As you know, this series of talks is organized by Al-Aqsa University in Gaza and by Academic Solidarity with Palestine. We deplore that the situation of internet in Gaza is such that many of our Gazan colleagues and many of the Gazan students who wanted to join us will not be able to do so. This is a scientific webinar, so it's lost for the great minds of Gaza and it's lost for science in general, but it will be recorded. Welcome to all of you. You can keep logging in. Please, I will introduce Terence Tao, and Dr. Simon Christensen and Dr. Julia Wolf will be the respondents. Please, for your questions, it's preferable to write them in the Q&A. There are two different chats, actually, the regular chats where you can send general messages and messages of whatever good fortune and happiness in general, and the truly scientific, the proper scientific question, actually, it's preferable if you write them in the Q&A, the separate chat for questions. So I will now introduce today's speaker, the distinguished Terence Tao. We're extremely privileged and honored to have him with us today. Terence Tao was born in Adelaide, Australia in 1975. He has been a professor of mathematics at UCLA since 1999. Terence Tao's areas of research include harmonic analysis, PDE, combinatorics, and number theory. He has received a vast number of awards, including the Salem Prize in 2000, the Fields Medal in 2006, the MacArthur Fellowship in 2007, the Crafoord Prize in 2012, and the Breakthrough Prize in Mathematics in 2015. Terence Tao also holds the James and Carol Collins Chair in Mathematics at UCLA and is a Fellow of the Royal Society, the Australian Academy of Sciences, the National Academy of Sciences, and the American Academy of Arts and Sciences. From 2020 to 2024, he served on the President's Council of Advisors on Science and Technology. And a great welcome to all of you. Above all, a huge thanks to Terence Tao for accepting to be here. And if we were all here, we would give you a standing ovation. And now, dear Terence, the floor is yours.
Well, thank you very much. I'm very happy to be here virtually at this event. It's difficult times everywhere, but particularly I think in Gaza and in that region, there's so much intractable conflict. Sometimes you wonder sort of what's the point of doing mathematics in such a time. But at least one thing that mathematics offer is that it is one place where we can actually resolve even very bitter disputes. We have a common standard of what things are true and what we're trying to accomplish, and so even mathematicians who disagree can eventually get on the same page. And I hope the same thing can happen elsewhere too. Okay, so I'll be talking about developments in my field, number theory, one of my fields, in the last decade or two, and in particular the subject of prime numbers, which is an ancient part of mathematics and one where we still have a lot of open questions today. So it's the field I study is a subfield called analytic number theory. It's concerned with the distribution of primes and things related to the primes, especially as you look at larger and larger scales. You look at what happens to the primes as the primes go to infinity. The way I like to think about the subject is that it's one of it's a struggle between two opposing features of the prime numbers. One is structure and one is randomness. So what do I mean by that? Well, it's best to illustrate with some examples. So the thing about this field in particular, analytic number theory, is that we have conjectures that are centuries old, and we have very good intuition as to what is true and what is not. We kind of know what to expect out of the prime. We have all these very precise conjectures, but we can only prove a very tiny fraction of them, even after centuries of effort. So here, for example, is a conjecture that's at least 300 years old. It's called the twin prime conjecture. So Euclid, already back in 3rd century BC or so, proved that there's infinitely many primes. It's one of the first theorems ever in mathematics, actually. But you change the problem a little bit, and you ask how many twin primes are there. So a twin prime is a prime p, such that p plus 2 is also prime. For example, 5 and 7 are twin primes. And this is an open question. We've tried for a long, long time, and we still can't find infinitely many primes that are twins, just as 2 apart. We have made progress. So in recent years, for example, starting with a breakthrough work of Yitang Zhang, who also built on earlier work of Goldstein, Prinz, and Yodom, we can find infinitely many pairs of primes that are not maybe necessarily distance 2 apart, but distance somewhere between 2 and 246. So we can get infinitely many pairs of primes with a bounded gap between them, but we can't push the gap down to 2. And that's actually a good reason why we're stuck. We may be able to improve the 246 a little bit, but we know we cannot get to 2 without a really new method. This is an old conjecture, but it's part of a much more general conjecture, which I won't write down here. There's something called the prime tuples conjecture of Hardy and Littlewood that doesn't just cover twins, p plus 2, but other patterns, p plus some constant h1, p plus another constant h2, up to p plus constant hk. And it doesn't just say whether there's infinitely many of those patterns or not, but it tells you how many there are asymptotically in a given range. So for example, for the twin primes, I guess I'll get back to that later. So what does this have to do with structure and randomness? So after Euclid's theorem, the next most fundamental theorem, then the next fundamental theorem is the fundamental theorem of arithmetic. Okay, but then the third most fundamental theorem in number theory is what's called the prime number theorem, which is counts how many primes there are up to a large number x. So this was conjectured by Gauss and Legendre and proved about 100 years ago, 120 years ago, that if x is large, the number of prime numbers up to x is roughly the integral of 1 over log t. So the way you should think about this is that if you pick a large number t at random, the chance that you picked a prime is about 1 in log t. So if you pick a large number n, then n is prime with probability about 1 over log n. N plus 2 is prime with probability also about 1 over log n. So if you believe that the primes are distributed very randomly, you might expect from probabilistic heuristics that the probability that n and n plus 2 are both prime should be about 1 over log squared of t. And from that, you would imagine that the number of twin primes up to x, if you apply the law of large numbers, which doesn't apply to the primes because the primes are not random. But if you believe the primes are what you call pseudo-random, that they behave like random numbers, then you'd expect the number of twin primes to be this expression here, the integral of 1 over log squared t. And this expression diverges, it goes to infinity as x goes to infinity. And so if this was the correct asymptotic, this would imply the twin prime conjecture. So this is a prediction coming from what's called the Kramer random model of the primes. Now, the primes are not completely random. So this argument is wrong. And one way you can see it's wrong is that the same argument would also show that there's infinitely many consecutive primes, n plus 1. But we know that we don't have infinitely many consecutive primes because the primes also have structure. So for example, almost all the primes are odd with only one exception, 2. And because of this structure that they all live inside the odd numbers with one exception, there aren't any consecutive primes other than 2 and 3. So this naive independence model, this random model is not correct, but you can modify it. You can take random subsets of the odd numbers rather than random subsets of all numbers, and that improves the model, makes it better. That still doesn't take into account the structure when you look at multiples of 3 or multiples of 5 and so forth. So, but we have ways of dealing with that too. So there's a more sophisticated model, which I won't completely describe here. It's called the Kramer-Granville random model. And it modifies this sort of naive prediction to give an updated prediction where you take the prediction of twin primes coming from pure randomness, which is this integral of 1 over log squared t, but then you add what's called an arithmetic factor, an arithmetic correction, coming from structure of the primes coming from divisibility of small primes. So the fact that the primes avoid multiples of 2, multiples of 3, and so forth. Each of those facts modifies the kind of twin primes a little bit. And so you actually take this integral and you multiply by a specific constant. It's called the twin prime constant, 1.32 something. So this is our prediction. And it's a really good prediction. You can get a computer to count how many primes or how many twin primes there are up to, say, 10 to the 15, and you get a certain large number of twin primes. And that formula I just wrote down you can compute that formula too. And they agree. I mean, they're not exactly the same, but they agree to extremely high accuracy. So this model is very reliable. And so we believe that this model is the truth. But we can't prove it. We can't prove that as you keep continuing this table, that the prediction coming from the Cramer-Granville random model will continue to agree with the to high accuracy to the actual reality of twin primes. The problem is that this model takes into account all the obvious structure of the primes, that the primes are odd, that they're divisible, that they co-prime to 3 mostly. But there could theoretically be more structure in the primes, some exotic structure that we're not aware of, and maybe only emerges past 10 to the 15, and maybe that extra structure changes this count in a weird way. And we have not been able to rule out these additional structure. So the fundamental challenge in the subject is to work out exactly how much structure is in the primes and how much structure is not in the primes. But we can make progress in the subject. And so in recent decades, there's been a lot of interesting advances and coming from a variety of techniques. I'll be talking mostly about the first type of. So there are inputs now coming from what a field called additive combinatorics, where you suppress the information about the primes and you deal mostly with combinatorial facts about addition. And that feels like you are removing information about the subject, about the problem, but you can actually make progress by taking this approach. There's a more classical approach called multiplicative number theory, based on the multiplicative structure of the primes, and in particular taking a generating function of the primes, which is related to what's called the Riemann zeta function. And that's a very classic approach. And we've also been making progress in this direction. And in fact, a lot of the most recent results proceed by combining ideas from both additive combinatorics and multiplicative number theory. These are by no means the only techniques we use in the subject. There are much more advanced methods that are also powerful. There's the whole techniques of orthomorphic forms relating to elliptic curves and eventually the Langlands program. And then there's also methods from algebraic geometry using the very deep work of Deligne solving the Rey conjectures, but I will not talk about these other methods in this talk. Okay, so let me talk about additive combinatorics. So additive combinatorics is the study of additive structure of various sets, combinatorial sets, such as sets of integers. And so you take a set of integers and you ask to study additive patterns inside the set. Maybe arithmetic regressions, maybe twins, and n plus 2. These sets could come from number theory. Maybe they're the primes or the squares or something that has to do with number theory. That subfield of additive combinatorics is older and it's called additive number theory. But the modern field of additive combinatorics generalizes beyond sets of number theoretic origin and tries to study arbitrary sets, like all sets that have a certain density, for instance. And the rather surprising fact is that sometimes to make progress in number theory, you actually remove the numbers. You remove the number theory, and you actually, instead of studying sets of primes, you study general sets that somehow look like the primes. And this is actually a surprisingly productive perspective. And one of the tools that has been developed in this field that has been quite useful are what are called inverse theorems. So we talked about the fact that sets such as the prime numbers can contain some randomness and some structure. And the whole problem is that these sets can contain unexpected structure. But there are these inverse theorems that give tests, they give criteria to check whether a certain set has unexpected structure or not. We now have ways that to check whether a certain set behaves randomly. And we can use those theorems, which come from combinatorics, combined with multiplicative number theory, and also some tools from dynamics, actually, to check that these extra structures don't actually exist in some cases. And that's how we can make progress on in this field. So to illustrate this sort of paradigm, I'll give some very ancient examples. So here's an example which Paul Erdős proposed, although his idea hasn't been completed yet. So there was this very old conjecture about the primes, that the primes contain arbitrary long arithmetic progressions. Okay, so 3, 5, 7 is an arithmetic progression inside the primes of length 3. I think 11, 17, 23, and 29 is a progression of primes of length 4. It was asked many years ago, I think in the 30s, whether there are arithmetic progressions of any length in the primes. And so Paul Erdős, as one of the most famous conjectures, he's famous for making lots and lots of conjectures in mathematics. And in fact, there's even a website that will hundreds and hundreds of his questions. In that website, which is run by Thomas Bloom, number 3, so the third conjecture on this website is this one. And I think this may be the first one that's still open, actually. That if you take any set of numbers, not just the primes, but it's any set which is large enough. And Erdős's definition of large enough was that if you take the sum of reciprocals of those numbers, they should diverge. Any set which has this property should contain arbitrary long arithmetic progressions. So one motivation for this was that he knew from a very old result of Euler that the sum of reciprocals of primes diverges. 1/2 plus 1/3 plus 1/5 plus 1/7, that sum does diverge very slowly, but it does diverge. So if this conjecture of Erdős is true, this would imply that the primes contain arbitrary long arithmetic progressions, and you wouldn't need very much information about the primes. This result of Euler, nowadays, you can prove it in one page to an undergraduate without, all you need is actually the fundamental theorem of arithmetic and the fact that the harmonic series diverges, the sum of 1/n diverges. This is a combinatorial approach to prove this result. Unfortunately, we can't prove this conjecture. Well, very recently there is progress. We can prove it for progression of length 3. We do know, thanks to work of Bloom, Sisak, and then also Kelly and Maker a few years ago, that if you take a set of natural numbers whose sum of reciprocals diverges, it does contain infinitely many progressions of length 3. But even 4, it's still work in progress. There are people who are making advances on that problem, but we're not resolved yet. In this case, we were able to, so Ben Green and I, about almost 15 years ago, we were able to, 20 years ago now, wow, okay, prove, in fact, that the primes do contain arbitrary long arithmetic progressions. We didn't exactly use Erdős's strategy, but we used some related techniques, which we're going to talk about a bit later. Here's another old problem in analytic number theory. It's consists what's called a Schnurmann's constant. So Schnurmann's constant is the least number C, such that every natural number other than 1 can be written as the sum of at most C primes. Okay, so 7 is already a prime, so you can write it in 1 prime. 8 is maybe 5 plus 3, you can write it as 2 primes. And there's an old conjecture of Goldbach, which, among other things, implies that this constant should be 3. Every number bigger than 1 should be the sum of at most 3 primes. That's a great problem. That's about as hard as the twin prime conjecture. We don't know how to prove this. We strongly believe it's true, but we can't prove it. But even back in 1930, Schnurmann was able to show that whatever, at least C is finite. And in fact, he was able to give a bound, but it was a pretty bad bound. C, he got 800,000. So he could show that every number is the sum of at most 800,000 primes. That's not a great bound, but it got improved over the years. So Ramire, for example, about 30 years ago, showed that C was at most 7. Every number bigger than 1 is the sum of almost 7 primes. The state of the art is 4. So Helfgott in 2013 was able to show that every number bigger than 1 was the sum of at most 4 primes. But I will talk about Ramire's method. So he used techniques from combinatorics. He used a little bit of number theory, but not much. So as I said, we have the prime number theorem. We know that up to x, there's about x over log x primes, roughly. If you compute that integral I mentioned, it's roughly x over log x. So this tells you some things about the sum of 2 primes. If you want to express numbers up to, say, 2x as the sum of 2 primes up to x, that gives you about x squared over log squared x ways to express numbers as the sum of 2 primes. But of course, there are repetitions. Let's see, I think maybe 13 plus 13 plus 3 is also 11 plus 5. Okay, some sums of 2 primes are the same. So there are collisions between these sums, but you can actually control the collisions. So using a part of number theory called sieve theory, you can count how many times a certain number can be written as a sum of two primes. And it turns out that a given number size x only has about x over log squared x ways of being written as a sum of two primes. This is a very slight lie, but on average, this is true. So that's the bound on the multiplicity of the sums. And so there's x squared over log squared x many sums here. The sums can only represent a given number about x over log squared x times. So you divide one by the other. This tells you that actually a constant fraction of numbers. So this really tells you that a significant fraction of numbers, maybe half or a third or something, all numbers must be expressible as a sum of two primes. So the set of sums of two primes has some positive density, maybe let's say a third at least. So how do you use this? Well, there are tools from additive combinatorics that if you know the density of some set A of integers, and you know the density of some other set B of integers, this tells you some information about the density of the sum set. If you look at all the sums of A plus B, there are inequalities that roughly say that the density of A plus B should be at least something like the sum of the density of A and the density of B. So if A has density 1/3 and B has density 1/3, you'd expect the sum set A plus B should density at least 2/3. Now, this is a lie, but some statements like this are true. I will oversimplify. So if A and B represent numbers that are sums of two primes, A plus B would represent the numbers that are a sum of four primes. And so you can iterate these inequalities a few times. And so Ramire did this computation very carefully and was able to iterate this observation and to get to the point where once you get up to 7, the seventh sum set you could show was actually density 1. It was actually the complete set of all natural numbers, actually. Okay, so how do we proceed in this subject to understand the primes? So the prime number theorem gives us the density of the primes, but it doesn't give us the location of the primes. So I said the number of primes. Consider the primes inside this interval from x to 2x. So I've represented it abstractly here by this big square. So this square you should think of as this big block of natural numbers. Let's say the numbers between 1 trillion and 2 trillion. So somewhere in here are the prime numbers, and so that's some subset of this square. So the prime number theorem gives us the density of that subset. It tells us that the primes inside the set has density about 1 over log x. So as x gets large, this is a very sparse set. So there's some strange-looking set inside this square, and that's the primes. And I've drawn it here to look like this kind of weird jellyfish thing, but it could, it could look like a random set of points. It could maybe have some patterns. We don't know. So the density is useful information, but it doesn't tell us everything we want to about the structure of the set. It only tells you its size. But we can add in additional facts about the primes. The primes are not just any old set of this density. For example, as I said, all the primes in this interval are going to be odd once x is bigger than 2. So you can divide the set of all numbers between x and 2x into the even numbers and the odd numbers, and that's a 50-50 split. And so the primes don't just are not equally distributed between the odd and even numbers. They only live inside the odd numbers. So actually the primes live down here. So this is a better picture of what the primes are doing. And the primes have density 1 in log x with respect to the whole integers. But if you restrict it to the odd integers, the density increases a little bit to 2 over log x. So they're a little bit denser. Still very sparse, but not as sparse as before. Now, we also know that the primes are coparameter 3 once x is bigger than 3 as well. So if you restrict the numbers that are coparameter 2 and 3, that's represented by this smaller rectangle. So that's a smaller subset of the prime, of the natural numbers. These are the numbers that are residue class 1 or 5 or 6. And here it turns out that the primes mostly live here, and the density has increased a little bit more to now 3 over log x. So you can start restricting using sieve theory. So we have just sieved out the multiples of 2 and multiples of 3, and we have increased the relative density of the primes relative to a container that we understand pretty well. So the set of numbers that are coparameter 2 and 3 is a very well understood set. As I said, it's just all the numbers whose last digit, base 6, is 1 or 5. So you can keep doing this. And so we have a century of sieve theory that is designed to do exactly this. And to cut a very long story short, what happens when you keep doing this trick is that you can eventually create this set of almost primes. If you remove the multiple of 2, 3, 5, and 7, and then you stop maybe at, say, x to the 1/10th. So it's like the Sievert Eratosthenes that you might have learned in primary school, but you stop it at some intermediate stage. You get what's called a set of almost primes, which are represented by this very thin rectangle. And so this is a set that we still understand pretty well. For example, we understand twin almost primes almost completely. And the primes are inside the set of almost primes. And now they're pretty thick. We understand their density. Their density is now not like 1 over log x or 2 over log x, but it's comparable to 1. So maybe it's like density 1/10. So it's now a fairly large set, a set that we understand pretty well. So this is what sieve theory gives us. It gives us this way of thinking, almost describing the primes. It's as a dense subset of a set that we understand very well. We also understand certain correlations. So it turns out if you do the analytic number theory, so if you do the additive combinatorics, eventually you end up using the Fourier transform, or what's called the circle method. It turns out the Fourier transform is very powerful for understanding the combinatorics of addition. And one of the objects that shows up in Fourier analysis are what are called Bohr sets. You take some irrational number alpha, like the square root of 2, and you look at a plane wave. E to 2 pi I n alpha, which I've abbreviated here as E of n alpha. And that's a quantity that goes around the unit circle. So you pick an arc in the unit circle, and that creates some portion of this set of all integers. A set of all integers, say, whose n, such that n times root 2 has a fractional part less than 0.5, for example. And that's some subset. That's called a Bohr set. You should think of it a bit like a residue class or an arithmetic progression, but it's a bit more general than that. So that's a set that shows up very naturally in the subject. And in particular, it's very good at detecting structure. So if a set if you're trying to count, for example, progressions of length 3 in a set, it turns out that there's an inverse theorem that tells you that you should get the same number of progressions as a random set unless it is this set is somehow very concentrated in one of these Bohr sets. So the Bohr sets I've described as this kind of vertical rectangle. And what we've been able to do is we've been able to understand how primes and almost primes interact with these Bohr sets. And the story is complicated, and it involves what's called a subfield of mathematics called homogeneous dynamics. But the upshot is that these Bohr sets are kind of orthogonal or independent of the almost primes. And then with a bit more work, they also turn out to be independent of the actual primes themselves. And that is an important observation, and that is what allows us to count various patterns inside the primes. So like one thing, for example, that Ben Green and I did back in the 2000s was that we discovered what's called a transference principle, that we are able to take the set of primes, which have very small density inside the whole space. They're very sparse, but we can actually approximate the primes in a certain sense by a much denser set. So it turns out that every sparse set inside this sparse almost primes, you can, in some sense, model or approximate by a dense set, or actually a dense function, to be more precise, on the whole space. There's a way to somehow average out all the restriction to almost primes, and you can transfer these sparse set of primes to a much denser set. The precise mechanism is quite technical and not suitable for this lecture, unfortunately. But the upshot is that because of this transference principle, if you can understand, if you have results, mathematical results about dense sets of integers, you can transfer them to also prove subsets about sparse sets of integers. And in particular, you can get information about the primes from information about dense sets, even though the primes are not dense. So this is one thing that Ben and I well, actually Ben was the first to introduce this. For example, there's an old theorem of Zemredi from the 70s that says that arithmetic progressions are very, very indestructible. It's very hard to get rid of arithmetic progressions. That if that you take any set of numbers that is big enough, so of some positive density, say density at least say 1%, it will necessarily contain infinitely many progressions. This result was also conjectured by Erdős and Turan in the 30s. This one got proven. the other conjecture of Erdős remains open. So this result doesn't directly apply to the primes because the primes of density is 0. But Ben and I were able to combine this theorem with this transference principle that I mentioned, and some additional effort, and you can actually show that the primes also contain arbitrary long progressions. Explaining why would take a lot longer, but this is the high-level strategy. In other words, so I mentioned the twin prime conjecture is still open, but we have this breakthrough work of Yitang Zhang, who was actually not a professional mathematician at the time. He was actually working in a sandwich store when he proved this. So he proved a near miss to the twin prime conjecture, that there are infinitely many pairs of primes that whose distance between them is bounded. His initial bound was like 70 million, but as I said before, it has now been reduced to 246. So the primes contain bounded gaps infinitely often. Now, this is a very deep result. It's not easy to prove at all. But in some sense, it morally follows from a much simpler result, which is the pigeonhole principle, that if you take, instead of the primes, if you take a much larger set, you take a set of positive density. If you take, say, 1% of the primes, 1% of the natural numbers, just from the pigeonhole principle, this set is forced to contain bounded gaps. It's a nice exercise for undergraduate students, that any set of density, say 1%, must contain a gap of size at most 100. There's a bounded gap, and the bound is inversely proportional to the density of your set. So the primes don't have densities, positive density, they have density 0, so you can't directly apply the pigeonhole principle to the primes, but in some sense, Zhang was able to adapt the pigeonhole principle to actually the almost primes, and use a version of the pigeonhole principle there. Although the idea actually is older, goes back to Gold's and Yoder. Zhang's contribution was to actually improve the sieve theory. Okay, so that is a very, very whirlwind tour of the additive combinatorial methods. It's a huge subject, but that was just sort of a taste. Let me briefly talk about the other another major tool that we use to study the primes, which is multiplicative number theory. So the primes are the multiplicative basis of the natural numbers. So we have the fundamental theorem of arithmetic, which is the second most important theorem in number theory after the Euclid's theorem. So every natural number can be represented uniquely as the product of primes. So you can represent that fundamental theorem analytically by taking a generating function. So you can package all the natural numbers together and do one function, the generating function of the natural numbers, which is called the Riemann zeta function. So for any number s, you take the sum of 1 over n to the s for every natural number n, and that's this amazing function zeta of s that we still don't understand as much as we would like. But all these numbers n are products of primes, and because of that, this generating function factorizes. So Euler observed, in fact, even before Riemann introduced this function, Euler was playing with it. He just didn't call it zeta. So this function actually factorizes into products of primes. That because every natural number n is the product of powers of primes p to the j, the zeta function actually factorizes into products of sums over powers of j, which are these geometric series, which you can sum using the geometric series formula. So you have this product representation of the zeta function, which is one way of thinking about the fundamental theorem of arithmetic. So you can already see maybe that from this formula that maybe the zeros of the zeta function will actually have something to do with the primes. So you can manipulate this formula a little bit. You can do what's called, you can perform what's called a log derivative. You can take logarithms of both sides and differentiate. And when you do that, you get another formula for, so this is called the log derivative of the primes of the zeta function. And that gives you a series. It turns the product into a series, which involves the primes. We normally write it in terms of a function called the von Mangold function, lambda, which is a function which detects primes. It is big. It's equal to log p when n is prime or power of prime, and it's 0 otherwise. There's an issue I'm glossing over as to what actually S is. Is it a real number? Is it a complex number? Is it positive, negative? That's an important question, but I don't want to talk about it. Yeah, on the other hand, zeta is a function of a complex variable. It has, you can apply tools from complex analysis and this log derivative actually has a partial fractions expansion coming from the zeros of the zeta function give you some partial fraction expansion of this log derivative. So you can write this log derivative as the sum of partial fractions coming from the zeros of the zeta function, which are traditionally called rho. So we have this relation between the von Mangoldt function and zeros of the zeta function. So you can transform this formula a little bit by taking some contour integrals and so forth, and you eventually reach what's called the explicit formula. That if you sum all the primes up to x with some weight, it turns out the natural weight is log p, that the sum of all the primes up to x is equal to x minus some additional correction term, where the correction term comes from zeros of the zeta function. So if you know things about the zeros of the zeta function, you know things about the primes. This is a really useful formula. There's an error term which is a bit complicated, which I don't want to talk about. Also, I'm cheating because this sum doesn't actually converge. So you have to truncate it, and then that gives you another error term. But this is, roughly speaking, the formula. Some mathematicians have given a poetic name to this formula. This is called the music of the primes. So if you actually plot each of these terms looks like a bit like a sine wave. And so this right-hand side is a superposition of sine waves. And this left-hand side is in some sense describing the prime numbers. So if the prime numbers were a sound wave, you would every zeta function would be every zero of the zeta function would be a note in this music. Although if you actually, I've actually listened to sound files coming from the primes. They don't sound very musical, but this is the metaphor. I actually asked an AI to generate to illustrate this for me. Actually, it worked really well. Actually, AIs are very good nowadays at generating code. This orange jagged line here, this is the sum of so this function summing all the log p's out of p less than x. This is called the Chebyshev function, psi of x. It's almost equal to x. If you look at the deviation between psi of x and x, it's this jagged orange thing. And the prediction, the music of the primes tells us that this error should look like this series. This is an infinite series. If you truncate it and you just look at the first 20 terms of the series, you get this. So this is the music. Okay, this is this oscillating sine wave type thing. Actually, 20 sine waves put together, basically, and it approximates the music of the primes, but it isn't exactly. It's an imperfect approximation because we only used the 20 zeros, whereas there's actually an infinite number of zeros that you actually need to add. But this already illustrates sort of how this formula could be potentially useful. It gives you some understanding of the prime numbers. So because of this formula, we would like to know more about the zeros of the zeta function. So for example, we know something about all these zeros. These zeros are complex numbers. We know that the real parts are always at most one. This was proven over 100 years ago. And by combining this fact with the explicit formula and a little bit of extra work, you can show the prime number theorem, that the number of primes up to x is roughly x over log x. This is another form of the prime number theorem. That the sum of the von Mangoldt function up to x is basically x plus a lower order term. Now, we actually believe a much stronger statement that actually all the zeros not just have real part less than one, they lie on what's called the critical line. The real part should be exactly 1/2. That's called the Riemann hypothesis. That's a problem that we really, really love to solve. But we are not close at all to solving this problem. This is a very famous unsolved problem in number theory. If we could solve this, we could massively improve the error term in the prime number theorem. It would tell us that the approximation x over log x, or the integral of 1 over log t, is actually really, really accurate. The error term behaves like square root of x. This is what we see numerically. If you actually plot the error term of the prime number theorem up to 10 to the 12, 10 to the 15, you will see this square root behavior. But we don't know that this pattern continues indefinitely. That is the Riemann hypothesis. So we can't prove that all the zeros lie on this line. We can prove that some of them do, and we can prove that many of them don't. So while we can't prove the Riemann hypothesis, we can make partial progress. And so one area in which we have made progress in recent years is to prove what are called zero density theorems. So given any real part sigma between 1/2 and 1, you can ask how many zeros are there to the right of sigma, where the real part is bigger than sigma. and maybe you also cut off the imaginary part to be bounded by some t. So you make some rectangle to the right of the critical line. The Riemann hypothesis asserts that there are no zeros in this region, and we can't prove that. But what we have been able to prove is that we've been able to prove non-trivial upper bounds. We've been able to show that there are not too many zeros in this region. So these zeros have a weird property. They repel each other like electric charges. Like if you take two positively charged particles, they don't like to be close to each other. They like to be apart from each other. And strangely, zeros in the zeta function behave a little bit like electric charges. They really don't like being close to one another. And you can exploit that fact. It comes from a certain orthogonality. You can exploit that fact to this repulsion of zeros to give upper bounds for how many zeros can fit inside a given rectangle. And so there are certain bounds for these numbers of zeros. They tend to go like certain powers of t to some power which depends on sigma. We would like this power to be as small as possible. Like 0 would be amazing. And in fact, the Riemann hypothesis tells us that this exponent should actually be negative infinity. But we can't do that. But we can get some bounds on this exponent a. So the smaller we can make a, the closer we can get to prove theorems about primes. For example, we can start finding primes in shorter and shorter intervals if we can bound a. So we have been able to make progress. So there's been dozens and dozens of papers over the years bounding a of sigma for various values of sigma. So for example, in 2023, the best bounds on a sigma is represented by this blue line. There's lots of different theorems stitched together here. But there was this particularly annoying value of sigma, 3/4, 0.75, where there was the best bound was I think 2.4, 12 over 5. And this bound had not been improved for 80 years, since the 60s, maybe 60 years actually. So there's the bound of Ingham and a bound of Huxley, but they met here, and there was no improvement for a long, long time, which is very frustrating because the maximum value of this quantity A controls a lot of things. There's a hypothesis called the density hypothesis that says that A should always be at most 2. We can prove that for some sigmas, but we can't prove it for other sigmas. But just this year, there was a major breakthrough by Guth and Maynard that they proved a new zero density theorem, which improved the bound on A sigma in this most difficult range. I also had there's some other improvements due to myself and Tim Tridgian and Andrew Yang, which are a lot less important actually. But but the big improvement was by Guth and Maynard. So they made the first improvement on this upper bound for A in 60 years. And so because of that, we can now localize the polynomial theorem to shorter and shorter intervals. We can find, for example, within any interval between x and x plus x to the theta, for almost any interval which is of this type, we can find a prime as long as theta is not too small. So theta at least 2/15. Previously, we could only do 1/6. So this is an improvement. We'd like to get down to 0. That's part of what's called the Kramer conjecture, but we are not there yet. So they're actually. So their proof is quite amazing. And again, I don't have time to talk about it here, but it uses techniques from harmonic analysis. So again, the idea is to kind of move away from the prize because we don't understand them very well and convert to a different area of mathematics where we can make more progress. So what I did is hard to explain in a few minutes, but they evaluated the Riemann zeta function at various test points. And so they evaluated this various partial sums of this series, and they needed to know when this sum was large or small, and it comes down to actually understanding a certain matrix. So these sums you can think of as a certain matrix multiplied by a certain vector. The matrix being a rectangular matrix where the entries are like 1 over n to it, where n ranges over some natural numbers and t ranges over certain other real numbers. And so most of the paper is dealing with understanding the size of this matrix, in particular the operator norm of this matrix. It turns out to be the important quantity. And they did something very clever. They controlled this the normal of this matrix by taking by using a sixth moment, which is normally this would normally be a completely um, inefficient move. So people often study the second moment. You take a matrix and you square it. Maybe the fourth moment, if you're feeling very courageous, m adjoint times m times m adjoint times m. But you almost never want to consider the sixth moment because it's so complicated. But they actually were able to do something clever with the sixth moment of this matrix. In particular, using some very clever Fourier analysis to get an amazing cancellation in this sixth moment. And they were able to use that to get a new bound on this operator norm. Now let's see, how much time do I have? Okay, almost out of time. I'll just mention one last direction which we make progress. So the prime numbers are hard to study, but there are some cousins of the prime numbers where we have been able to make some progress. So there's something called the Liouville function, which is related to the primes. It's a function that's either plus one or minus one. It's plus one when you're the product of an even number of primes, and minus one when you're the product of odd number of primes. So it fluctuates kind of randomly between one and minus one. And if you actually look at it, it looks like a random sequence. And there's a principle called the Liouville pseudo-randomness principle, which asserts that this function behaves like a random sequence of ones and minus ones. For example, if you take its average value, its average value should be zero, which actually turns out to be equivalent to prime number theorem. So this randomness principle is very similar in spirit to the randomness that we expect from the prime numbers, but it's simpler to describe. And we've been able to make more progress on the Liouville function than we have on the primes. So for example, I just mentioned this work of Guth and Maynard that were able to control primes in intervals of length x to the 2/15. There's a breakthrough work of Kaiser Matamaki and Maxime Radziwill about 10 years ago that the Liouville function, we can actually control average values now on really, really short intervals. Like you just take intervals between x and x plus log x. They were able to show that in almost all the intervals, the average value of the Liouville function is zero. And that's, they used really, really clever multiplicative number theory. So they really manipulate the zeta function using complex analysis quite cleverly. And we've been able to use those facts to prove things that begin to resemble the twin prime conjecture. So the twin prime conjecture relates to the primality of n and n plus 2. We can now relate to the Liouville number of n and say n plus 1, also n plus 2, if you like. That we can show that on average, the Liouville function of n and the Liouville function of n plus 1 are uncorrelated in a certain technical sense. There's a certain weight that is annoying, but we're stuck with it. And so we've been able to get some slightly non-trivial bounds on these sort of correlations. And there's been also recent work improving these bounds by a fair bit. I think the state of the art is now you can get log x to 1 minus a small constant. So one of the things I'm working on right now is to try to extend these bounds to higher order correlations. So the target here is something called the Charler conjecture, which conjectures that any k-point correlation function should asymptotically be zero. This is the analog of the prime tuplets conjecture. So proving this would maybe be a stepping stone towards the prime tuplets conjecture, which would also imply things like the twin prime conjecture, maybe the Goldbach conjecture. Lots of other notorious conjectures in number theory are blocked because we can't solve this one. So this one is open, although we are getting closer here too. There is some very nice work by Walsh, but recently, but there's no time to talk about that. So I will stop here. Thank you very much for your attention.
Thank you so much, dear Terence Tao. I am really sorry. As you were finishing your speech, I realized that I was writing only to panelists and instead of sort of welcoming and cheering everyone. Thank you so much. This was extremely enriching. For all of you attendees, please send your questions to Dr. Tao on the question and the specific form for questions. I will now leave the floor to Julia and Simon, who will pick up on the scientific discussion. Thank you so much again.
Thank you, Christine, and thank you so much, Terry, for this wonderful whirlwind tour of analytic number theory. Please do keep sending your questions in. So we have one at the moment in the Q&A. So why don't we use that one to get started? So do you have any suggested texts or references for somebody to get started in analytic number theory?
Yeah, there are quite a few. When I was a student, actually, a good friend of mine, Sandra Rajan, who's also a number theorist, he sent me his as a birthday gift a copy of Tom Apostle's Introduction to Analytic Number Theory. So that book is quite yeah, maybe it's out of date now, but I enjoyed it very much. It was very suitable for a high school student. There's a book by Paul Pollack, I think it's called Not Always Very Deep. And it's a very accessible, friendly introduction to number theory. If you want to go more advanced, there's a textbook by Davenport called Analytic Number Theory. And then there's a series of two textbooks by Montgomery and Vaughan called Multiplicative Number Theory. The first one came out in the 80s or something, or in the 90s. The second one is Vaughan is just finishing it this year. I think he finally got around to finalizing the second volume. So that's also a good resource. Then there's a very advanced text by Ivanish and Kowalski, but that I think is not for beginners.
Thank you. I hope we captured those references. Maybe I can type them up after the talk. You also maintain a blog where you have posted lecture notes from or summaries of your lectures on analytic number theory. Sort of, would you recommend those to students in the subject?
That's true. I do have a blog. It is primarily aimed at sort of graduate level students, but some of my articles are more accessible to, say, undergraduates as well. And I even have a few popular science type articles. So I do have lecture notes on my own. I taught analytic number theory, and I put and several other courses, and I put my lecture notes on my blog. If you just type my name and my blog in the search engine, you'll find it.
Okay, fantastic. So we have a few more questions coming in. Simon, did you want to pick one?
I just wanted to pick the first one, really. The first one is, I work on Fibonacci primes. Any references you recommend?
Yeah,
I'm very interested in that because I have personally no idea.
That's a good question. Yeah, we know very little. The thing about Fibonacci numbers is that they're a very sparse set. They go exponentially. And our understanding of prime numbers on very sparse sets is very weak. In fact, even much denser sets we still don't know. So there's a old conjecture of Landau that numbers of the form n squared plus 1, square numbers plus 1, are there infinitely many primes of the form n squared plus 1. And that question is still out of reach. It's a harder version of the twin primes conjecture. So Fibonacci numbers, they're like golden ratio to the n, and they go exponentially fast. Then, of course, there's Mersenne numbers, 2 to the n minus 1, which are much more intensively studied. And in many ways, Fibonacci numbers and Mersenne numbers are very similar. So one is 2 to the n minus 1, and the other is golden ratio to the n minus something. Maybe divide by the golden ratio again. So there are some things that are known. So like Mersenne numbers, we know like a lot of them are co-prime to each other and things like that. So I think there are some other aspects you can transfer to Fibonacci primes. There are certain tests for primality for Mersenne numbers. There are fast ways to test whether Mersenne numbers prime. I can imagine you could adapt them to Fibonacci primes. So yeah, my recommendation is to learn about Mersenne numbers because there's a lot of literature there, and maybe some of that can be carried over.
Excellent, thank you. Our next question concerns Fermat's last theorem, which created a huge splash and used very different ideas. Are there any connections at all between sort of the ideas you talked about and those that are present in Fermat's last theorem?
Yeah, the mathematics is very different from Fermat's last theorem. So it's all based around elliptic curves. There's an amazing connection, I think, worked out by Frey. Solutions to Fermat's last theorem, A to the n plus B to the n equals C to the n, surprisingly generate a very interesting type of elliptic curve. And then there's a whole extremely advanced science of what types of things you can do on elliptic curves. The tools from additive combinatorics, so Fermat's theorem is about the sum of two powers, like sum of two cubes, sum of two squares, or sum of two fifth powers. If you sum many powers, then additive combinatorics becomes useful. Like if you want to represent a number as a sum of 5 squares or 28 cubes, then methods from additive combinatorics, and in particular this thing called the circle method, is very useful. But additive combinatorics actually struggles very hard with what we call binary problems, writing numbers as the sum of two expressions. Yeah, so there's this even go-back conjecture that every even number bigger than 6 is the sum of 2 primes. And for various technical reasons, our techniques do not work for binary sums. 3 and higher is when we start getting good results. So unfortunately, our tools do not overlap. There is some connection though. So there's something called the ABC conjecture, which relates, if you have 3 numbers A plus B equals C, there's a conjecture about how the factors of A, factors of B, and factors of C relate. It would imply most of Fermat's last theorem, but it's not proven. There are claims to be proven, but they're controversial. But you can use methods from additive combinatorics to show that the ABC conjecture is mostly true, that the set of exceptions to the ABC conjecture is actually very small. And there's been some recent progress there using, well, actually not quite additive combinatorics, but geometry of numbers. It's a related field. So there is some connection there.
Thank you.
Thank you. Excellent. Simon?
Next question. The next question relates to the final part of your talk and the zero estimates. Does one expect the same kind of zero estimates for L functions?
Oh yes, okay. I can see you already know something about the subject. Yes, so the zeta function is just it's the most famous member of a larger family of functions called L functions. And the belief is that, so the zeta function just captures information about the primes themselves, just the size of the primes. L functions also capture things like how the primes behave in residue classes, like whether the prime is equal to 1 mod 4 or 3 mod 4, things like that. And it is believed that everything that we think is true about the zeta function should also be true about the Dirichlet L functions. For example, the Riemann hypothesis is a statement about the zeta function. There's something called the generalized Riemann hypothesis, which is a similar statement for L functions. So yes, it is believed that so many of the zero density theorems that I mentioned have been extended to L functions, but the proofs are more delicate and more complicated. I think the Guth-Maynard one has not so far yet been extended to L functions, but it will just be a matter of time. I think the techniques look very transferable.
Thank you.
So we have another question asking for advice, this time not on references for newcomers to the subject, but any tips on writing up solutions, I guess, to problems, or possibly writing up one's own results, which is, of course, always a learning process.
This is something which we don't teach very well, to be honest. If you go to a university and you go to a math class, the emphasis is mostly on theory and doing calculations, and you add up your homework, but often the emphasis is as long as you got the right answer and you kind of wrote down the key steps, we don't pay much attention to sort of how well you explained your thought process, and that's a shame. I mean, mathematics is a social subject. It's not just about solving problems, but also about communicating what you do to other people, and so you have to tell a story. A good story, should have various narrative elements. There should be a good guy and a bad guy, and then some dramatic tension and a plot twist, like if you were watching a movie and all it was just showing what happened, here's a dog, here's a car. If the car goes over here, it'd be completely boring if there wasn't a story. So yeah, it's something that you sort of learn. I mean, I actually only learned this after grad school. I mean, my writing was initially quite terrible, to be honest. And it was only after seeing other people give really good talks or write really, really good papers where I realized that it's not just how impressive your results are, but so what story you tell. Maybe writing, like if you do writing in other spheres, like if you write an essay for some humanities subject, or you chat on social media, I think, or if you like reading or you like watching movies, I think understanding just how to tell stories in general is useful.
So I completely agree with you. Let me just take that a little bit further. Do you think as a discipline we have chosen the best way or the best medium for telling our stories? Because I think, there's often a big difference between what you hear people talk about, the way you hear people present their result in a talk, and the pictures they draw and the pictures that they have in their heads when they're thinking about mathematics, and what you see in the actual paper.
Right. Yeah. So mathematicians are very traditionalist. We've been doing things the same way for hundreds of years. We publish in journals that are 100 years old. We still use blackboard and chalk in our offices, and almost nobody else does. Yeah, I think we haven't moved with the times as much as we should. Yeah. So in particular, we teach math through textbooks and papers, and in those papers, it's very dry and it often doesn't tell a story. In particular, like when you solve a problem, there's all these false starts and trial and error, and something doesn't quite work, but you fix it, and you see almost none of this process when you read a paper or a textbook. You only see the final finished product, in which all the mistakes have been edited out. In a talk, you might get a little bit more. Maybe the speaker will open up a little bit about tell a story, but still we don't do enough of that. I hope we're beginning to get these more open projects where they're on the internet and people can see the discussion going on before the results are proven, and you can get more of a glimpse into the actual process, and that I think is more narratively interesting. But still, part of it is because I think it's human nature. We don't like to show our mistakes. Because behind every correct proof, there's like 10 embarrassingly bad mistakes that you made before you actually found the correct solution, and we don't like sharing those with the public. But maybe we should be a bit more open about that.
The 10 mistakes would save us an awful lot of time by making sure we don't make the same ones.
Right, yeah. So I think Dirac or some other, or Bohr, Niels Bohr, who was a physicist, once said that an expert is someone who has made all the mistakes that can be made in a very narrow field. So there's certain mistakes that actually everyone sort of has to make as part of their training, so that they never make them again. And so, yeah, maybe we should actually encourage the freedom to fail, to actually play with things and actually make mistakes, but view them not as shameful, but as learning experiences.
I read somewhere about somebody who made mistakes, but good mistakes.
Yeah.
Definitely quality to mistakes.
Yeah, no, I mean, no one's perfect, and this is how you learn through. If you always have the correct answer, there are students who are very, very good at math at a young age. I was excited myself, and there's this trap that actually, if everything comes easily to you and you don't make mistakes, you don't grow. And at some point, the subject gets harder, and at some point, your natural talent doesn't get you so far anymore, and you can struggle. Whereas people who encountered difficulty earlier and developed more skills to solve problems, they actually can do better in later education than people who were gifted in the early years.
I mean, aside from actual mistakes that one makes, there are also many attempts at proofs that simply fail because, you know, we discovered that they couldn't have worked to start with. I mean, maybe this is what we were talking about a little bit, right? I think that is also something that we don't see enough of in public forums, because everybody who works on this problem has to go through the same process again to sort of rediscover why sort of the obvious thing that you would try doesn't work. So I think in that context, blogs like yours and those of others have a sort of big role to play.
Yeah. There's a lot of folklore that maybe an advisor tells their student in a one-on-one in office, but we don't write down in our books and papers. You know, so you're right. There's a lot of implicit knowledge, and with the internet, that we do have the ability to share a little bit more broadly.
There's one more request for book recommendations. This time for beginners in number theory.
Right. Yeah. So it's I can give the same recommendations. Yeah. So Pollock's book and Apostle's book, quite good. Yeah. There's actually even on YouTube. There's some very good math bloggers. Numberphile, for example, has a lot of videos on prime numbers that are quite good. Phoebe One Brown has a great video explaining the Riemann hypothesis. Yeah, and there are math forums on the internet too. Yeah, I think it depends a lot on one's background. I think there's no one best book that everybody should read. It sort of depends on what you like doing. You know, if you like working with computers, there are books that are very computational. If you like pictures, there are books that are very visual. It depends on the individual.
So we have a question here relating to the twin prime conjecture. So why is it formulated as you want infinitely many primes that differ by 2, as opposed to some other arbitrary fixed gap n?
Yeah. So there's nothing too special about 2. 2 is just the smallest gap that could occur infinitely often. Gaps of size 1 cannot, because primes are almost always odd. But the expectation is that if we ever solve the twin prime conjecture for 2, we would also solve it for 4 and 6. Okay, so the gap should always be even. So after the first gap, 2 and 3, all gaps are even. But there's a broader conjecture called the Polyniec conjecture, that every even gap appears infinitely often. Yeah, so 2 is just the most famous example. But we don't expect anything particularly special about 2. But on the other hand, they're not related. If you prove infinitely many primes of gaps of form 2, you don't immediately get gaps of size 4. There's not a logical relationship.
There's not. Yes, there's no direct implication. Yes, but you would expect the method of proof to give you that as well, right? Because this is the kind of problem that suffers from this binary difficulty, and then you have 2 linear forms that are directly related, right? So in that sense, they are the same. Yeah. Excellent, thank you.
There's a question about one of your last slides. That must be the slide about the Liouville function.
Let's see.
I'm trying to find it again. Maybe it was the second to last slide.
Yes, I think it's this one.
Right.
I think it's this one. Yes. It's about the H, which was just log of x.
Okay. Okay. Right. Yeah. So so this is about the Liouville function rather than the prime numbers. So the prime numbers they get sparser and sparser. So the gap between adjacent primes actually is expected to get larger and larger, like log x. And this is one reason why it's hard to find twin primes, because those are pairs of primes where the gap is much smaller than the average. But the Liouville function, the gap, so that's a function of plus ones and minus ones. And there, the gaps are expected to be bounded. So the Liouville function flips between plus 1 and minus 1. And half the time is plus 1, half the time is minus 1. So the gap between consecutive plus ones, so these are numbers which are not primes, but products of an even number of primes. The gap between those numbers are expected to be of bounded size. What mathematical advancement showed was that if you take any window which is bigger than bounded, so like an interval size log x, that window is big enough that it will contain about 50% plus one and 50% minus one. In a way, it's saying that the gaps between values of plus one or values of minus one should be roughly bounded on the average.
Right. Sorry.
So our next question concerns a topic that I know you have thought a lot about. You know what's coming. Which is, has AI been used to tackle any of these open problems in analytic number theory?
So almost anyone mathematician who has played with these tools, one of the first things they will try is please give a solution to the Riemann hypothesis or something. And it will either say, no, I can't do that, this is an impossible problem, or it will come up with some complete nonsense, hilarious actually. So far these tools have not been super useful directly. There are slightly older types of AI. So there are these things called neural networks that you can feed it a lot of data about various things, and it can pick patterns from that you might not have seen in the data set. So there's in the study of elliptic curves, there was this phenomenon called murmurations. I forget exactly what it concerns. I think like the fluctuation in the number of points on an elliptic curve. And it was a pattern that was first discovered network, if I recall correctly. So people just collected big data sets about elliptic curves and ran it through a neural network, and they found a pattern which has since had at least some partial theoretical explanation. So that is one area where I see AI could be useful, is by doing experimental mathematics. In fact, the prime number theorem itself was first discovered experimentally. Gauss and Legendre actually computed by hand, and I think they paid some people to help them to build a table of the first 100,000 primes. And through that data, they conjectured the prime number theorem. So there's actually a long tradition of experiment being used in number theory. So there is where I think AI will be very helpful. Another direction which I think will be useful is, I mentioned these zero density estimates. So this is very complicated curve of zero density estimates, and they're formed by piecing together lots and lots of little sub-estimates. So there's lots of other related inequalities, and people have just been very clever in combining the correct combination of putting together 10 different other inequalities in just the right way to generate these zero density estimates. But it's a very tedious process, lots of trial and error, and people make mistakes. And the whole process could be automated. That you could just have this big database of relevant estimates about exponential sums and the Fourier transform and so forth. And you can imagine in the future some AI would just mindlessly combine all these things together and just optimize every time a new estimate is proven, that you just dump it into this sort of soup of estimates, and it would just automatically update graphs like this without having to manually do a lot of tedious calculations by hand, which is the current state of the art. We are not very computerized right now, but we should be.
Sorry to interrupt. Let's have just one more question, and I think we'll wrap up for today. As I said online, the talk will be uploaded on our dedicated YouTube channel. But let's take one more question. Simon and Julia, you choose the most finely tuned and appropriate one, and then we will wrap up. Thank you.
Maybe I'll slightly paraphrase one of the questions that I see in the Q&A. So have you ever found it useful to sort of borrow from kind of other fields of science in your thinking about mathematics?
I very much think in analogies. For example, I view discrete and continuous mathematics as very related. If you study some discrete so like the primes, if you look out at a very large distance, I think of it like a continuum. It's just like physical matter is made of atoms, which are discrete. But if you look at a very large scale, it can behave like fluids. I do have a result about the zeros of the zeta function. There's something called Newman's conjecture. There's a certain transformation you can do to the zeta function. You can make it solve what's called the heat equation, and this moves all the zeros around. In particular, it was conjectured that once you apply this procedure, you would move the zeros off the critical line. I was able to prove this with actually a former student of mine, Brad Rogers. And the intuition actually was that I viewed these zeros as like particles, which could be in various states. They could be in like a solid state where the zeros behave like an arithmetic progression. They could be in a liquid state where they stayed on the critical line, but looked very random, like some zeros are close and some zeros are far apart. And then there's this sort of gaseous state where they fly off the critical line and do crazy things. Applying this heat equation deformation to this zeta function actually was very analogous to heating this body of particles and turning them solid to liquid to gas. So actually, having some intuition from thermodynamics actually really helped solve this problem. We introduced some things that look a bit like entropy and differentiated that. Yeah, I mean, I had seen these sort of things before. There's another field of mathematics called randomnicics theory, which actually is also related to the zeta function. But yeah, certainly I at least have found that knowing a little bit about everything, all the other sciences is really useful. Physics most obviously, but life sciences, social sciences, computer science, yeah, it's all useful.
Wonderful, Terry. So on behalf of the audience, let me thank you again very, very much for your talk and your willingness to share your thoughts about this very fast-moving area, which continues to be extremely interesting. Yes, I hope that everybody has enjoyed the session today.
Yeah, it's a pleasure to be here.
Thank you so much. Indeed, from all the long list of thanks in the chats, you can be sure that everybody enjoyed it. In the meantime, I got some messages from our colleagues in Gaza. Unfortunately, they could not join, but they are with us in spirit. Again, we deplore the situation such that they could not join us, but Gazan universities are alive and well, and it is thanks to them that we had the chance to have Terence Tao with us today. We will let you know when the talk is uploaded on our channel. We will send you notifications for the next ones to come. And above all, thank you to all the attendees who came, and to Julia and Simon, the respondents, and above all to Terence, who did this brilliant talk. To the panelists, I will write to you separately in the email, but it's huge. It's immensely important for Gaza, for Gazan science, and for Gazan universities. Thanks again to all, and we will be with you very soon again. Thank you.
Okay. Thank you.